Before we start talking about the integral test, we need to kind of look at what it means. What does it mean here to be called a sequence and to be called a series? And so we know a sequence is really a list of terms. So we start with our first term, and then we have our next term, and our next term, and our next term, and so on. As we approach, and so on, as we approach the infinite, or the a sub n term, and so we know we're really looking literally at a list of values. And so if we think about what it means to have a list of values, really, and we talked about this in the first section, is really we can say, well, that list of values is really the values we get from the a sub nth expression, and it really can be considered a function. So if we're looking at this, we can say, well, we have this first term here, and we can really write this first term as the ordered pair 1 comma a sub 1. And we have this second term here, and we can really write that second term as 2 comma a sub 2. And the third term is a sub 3, and so on and so forth. And so we can really kind of look at a sequence as a table. There's the sequence number, first, second, third. Here's the value of the term. So this 1, 2, 3 is referring to the fact that this is in the first location, this is in the second location, this is in the third location, and the A1, A2, A3 are the values of those terms, and those values of those terms are based on some a sub n pattern. And so that's why we can really refer to a sequence as nothing more than a function, and why we can then say, well, if it's nothing more than a function, then we can treat it just like a function from the standpoint of determining its limit. And so we can then talk about things like, what value does this go to? For the majority of the sequences that we look at, we're gonna look at things that are monotonic and bounded. And if we're talking about being monotonic and bounded, and we're talking about something like a sequence here, then what we're looking at really is these individual location, or individual points really on this graph. And so if this is our first location, this is our second location, this is our third location, and so on. Then what we have here is, we have that specific value a sub 1, and we'll just call it maybe right there. So there's the value a sub 1, and it represents the first term of the sequence. The value a sub 2 might be here, and it represents the second value in the sequence, and the value a sub 3 maybe is about right there, and so on and so forth. So if we look at these values, here's a sub 5, there's a sub 6, dot, 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 maybe a sub n is way down here. So if we look at these individual values, these are the individual values of the sequence. And then we can see that in this case, this is a non-increasing pattern. In other words, it either stays the same or decreases. And it's bounded by some lower bound here that is, it should be a sub n, by some lower bound here that we haven't determined yet because we're just talking about a general sequence, so we don't really have anything to calculate the limit of. But we have some sort of lower bound here. And likewise, we could have a sequence that would be monotonic, and if I can just duplicate this here, we could have a sequence here that instead of being monotonic and decreasing, we could have a sequence that is maybe monotonic and increasing. So, something that looks like this and looks like this and gets bigger and bigger and bigger, and so on and so forth. Where here's our E sub 6 looks like it's a little out of place, but you get the idea, kind of, where we have this monotonic and increasing, where this is my value of A sub 1, and this is my value of A sub 2, and so on and so forth. Okay, and so of course the monotonic and increasing, we could safely say, since this has some sort of lower bound in this picture, this would go to infinity. We could also have it monotonic and increasing to an upper bound here as well, so kind of curved in that nature. So we've got a couple of things to kind of look at as that as we kind of further define that what a sequence is, and we very much can just say it's just a function. On the other hand, a series, we're talking about taking this sequence and adding up the terms. So we're talking about, and we can write this a couple of different ways. We can say, well, a series is we're looking at the sum of all of these terms. So we can say our series then is, if we want to write the series, we're looking at a first partial sum, a second partial sum, a third partial sum, a fourth partial sum, and so we're really looking at taking that first term and adding the second term, and adding the third term, and adding the fourth term, and adding the fifth term, and so on and so forth, all the way up to that infinite term. And so when we talk about a summation then, and we want to talk about that graphically, we can kind of take a look at that by using this same picture we have right here. And so if we look at this picture of a sequence here, of our sequence values, now instead of looking at the individual values here, what we're saying is we can look at these, instead of looking at these individual values here, and I'm just going to kind of get rid of the values, we could say, if we take a look at this first term, A sub 1, that is this value here, but if we're talking about a summation, then we're talking about adding up this value and this value. And so for a graphical representation of that, we can look at then a rectangle here. And the reason why we can look at this rectangle is because if we start drawing these rectangles between these sequence numbers, they all have a width of 1. And so if we're looking at this rectangle here, which has a width of 1 and a height of a sub 1, then that's the value of the first term. And then we can look at this next rectangle here. And that next rectangle has a width of 1 and a height of a sub 2. And so if we add these two rectangles together, we get the value of the second partial sum. And we can keep going through here and take a look at the next rectangle here with a width of 1 and a height of a3. And if we add up these three rectangles, that's like adding 8 terms 1, 2, and 3. That's the third partial sum. And so on and so forth. And you probably are starting to see the pattern already, even before we start talking about it. But there's the fourth rectangle and the fifth rectangle, width of 1, height of a sub 5, and it just continues on. And of course, whenever we add up rectangles in calculus, we're talking about a Riemann sum. And so for this Riemann sum here, as we continue to go on here, we're looking at a Riemann sum that ends up being a right Riemann sum. And if we kind of overlay the sketch of the function that is represented here, you know, this function here that we can represent the sequence with, then this function really instead of adding up infinitely many rectangles, we can say, well, if we just look at the function, we can then integrate the function and we can see whether or not we can get a finite value here. For the area. And if you so what we're getting to then is we're using an integration process. And if we have this, if we have the area here that I would color in green, if we can have the area here that we find by calculus, and let me see if I can kind of make that a little more transparent here so that we can see through it. Yeah, I think I can. There we go. So if we calculate using integration the area here underneath the curve, like we would typically do when we integrate in calculus, and that's a finite value. If you notice the values here for the that represent the terms of the sequence, which would be all of these values underneath these rectangles here that represent the terms of the sequence. All of those values are smaller than the area of this curve. So we know that if we can get a finite value for the area of the curve, then if we were to add up all these rectangles, since the rectangles are right sums, if we add up all those rectangles, which we can represent by saying this, then that area, quote unquote, or that sum is going to be somewhat smaller than the integral of the function that we could calculate. And so if this is a finite value, then the actual sum, whether we know it or not, must also be a finite value. And so what we can do then is use this process of integration to determine whether or not we have convergence or divergence by just looking at the value of the area under that curve and knowing that the actual sum lies within that area. So before we go to the next page and talk about using the integral test, one thing that's worth noting is that the integral test is really a test that we use on these monotonic non-increasing functions. Okay, this type of function that's monotonic and non-decreasing, whether it looks like this or it looks like this, all of those rectangles continue to get taller and taller and taller. And so for our monotonic non-decreasing, since those rectangles are getting taller and taller, we know that the sum must be infinite, because all we're doing is adding more taller and taller rectangles. So so we need to have a monotonic non-increasing okay, so something that looks like this graph in the red, where we have subsequently smaller rectangles. We can stand a chance at maybe getting a finite value. So here the rectangles will get shorter. And now when we integrate here, integrating here, we're going to definitely get infinity. Integrating here, it's a question mark as to whether or not you get infinity or a finite value. And we'll talk more about that as we go on through this section as to how to make that determination. We can either get this or this, but at least we can integrate it now and see whether, kind of see what direction it goes in. So when we take a look at that, that's the characteristic we're kind of considering, is we have to have this non-increasing function. For instance, here, we start with this function increasing and then it's decreasing, but when we're talking about over the entire length of this function all the way up to the a sub n term, if here is our a sub 1 term, we're really talking about getting the non-increasing characteristic starting with the, looks to be second term. And so when we're talking about, whether or not we should let this be a non-increasing function, the answer is yes, because we're really only talking about adding the value of one more term to that when we talk about integrating this. So, so the integral test basically says if we have a series and we can rewrite it as a function and take the lower and the upper bounds and plug it into the function and get some finite value, this equals some finite value, we'll call it L, then we get convergence. If it equals infinity, then we get divergence. Okay, and so we have to remember that, when we get a finite value, when we integrate that, that's considered a convergent function, and when we get infinity, it's considered a divergent function. So when we look at integrating this, this is an integration by parts. So this is where the chapter on integration techniques really pays off. So we're going to take that integration by parts and go ahead and split it up. So u is going to equal, let's write this as a function first. Well, so if we write this as a function, it's x e to the minus x over 2. So we'll let u equals x, and then dv equals e to the minus x over 2. That means the derivative is dx, and when we integrate this, we end up getting minus 2e to the minus x over 2. And so coming up with the integral, then that's u times v minus the integral of v du. So u times v is x e to the minus x over 2 minus, and then we're going to integrate this, minus 2e to the minus x over 2 dx. And finishing that off, we get xe to the minus x over 2. I'm going to factor out the negative 2. And then I'm going to go ahead and integrate that again. So that's going to be another negative 2e to the minus x over 2. So after integration by parts, we get xe to the minus x over 2, not plus, because we've got another minus sign there. xe to the minus x over 2 minus 4e to the minus x over 2. And so we I think I dropped a 2 somewhere, u times v. Yes, I did. I should have a minus 2 out here. U times v should be a minus 2 out here. So I just forgot to put in the minus 2. And so we have to evaluate that between 1 and infinity. And really now we're talking about an improper integral. So really we need to take this infinite limit and set it equal to a variable. We'll call it b. And so we have minus 2x over e to the x over 2. I just want you to kind of be really certain that that's in the denominator. Minus 4 over e to the x minus 2. And so we're going to evaluate that from 1 to b. And so we have minus 2b over e to the b over 2 minus 4 over e to the b over 2. And then we have minus negative 2, because 2 times 1 is negative 2, e to the 1/2 minus 4e to the 1/2. So we're taking the limit that as b goes to infinity. And so as b goes to infinity, we're taking a look at this. The top goes to infinity, the bottom goes to 0. Excuse me, I said that wrong. The top goes to infinity. The bottom goes to infinity, but e to the infinity is much bigger than infinity, so this ends up being just basically 0. And 4 over infinity is 0. And then if we look at this, then we have evaluating this, we just have then minus 6 over the square root of e, basically. So the limit here ends up being 6 divided by the square root of e, which is a finite value. You know, we can grab a calculator and figure out what that value is. So if we would do that, we would just kind of, I'll have to grab my graphing calculator here. There we go. And so we take 6 divided by the square root of e, and we actually do have e here, so I'll put e right in there. Don't need to know the value. And 6 divided by the square root of 3 is about 3.639. So approximately 3.639. So it's a finite value. So we have then just a general statement here that since the integral of xe to the minus x over 2 dx is approximately equal to 3.639, which is finite, then the series n e to the minus n over 2 converges to a finite value. And again, going back to that previous page, we don't know the value. We know that the value of the integral, okay, so that would be the green area, we know that is about 3.632. So this area in here, starting at 1, this area is 3.632. Okay. The actual series is that right sum underneath here. And so what we're talking about then is, that basically that lower sum, which means we start doing a right-hand sum with term 3. Excuse me, with term 2, we start doing a right-hand sum. Even if we did a right-hand sum with term 1 and overestimated it, it wouldn't nearly add up to all this extra space underneath here. So we know that the actual sum of the series is something smaller than that. And we don't need to know the exact value. We're not being asked to find the sum, but we know it's finite because we know it's somewhat smaller than the area underneath the curve. So likewise for this one, we have this series here. So we have 1/3 plus 1/5 plus 1/7 plus 1/9. So if we look at this, we're talking about, here's 1/3. So here's that a sub 1 term, 1/3, and here's 1/5. So there's the a sub 2 term, and here is 1/7. There's the a sub 3 term, and so on and so forth. So coming up with an nth term here, we've got we're looking at making odds, and I said one of the two ways to make an odd was either 2n minus 1 or 2n plus 1. So for the first term, this would give us 1, this would give us 3, it must be a 2n plus 1 pattern. And so we're looking at adding up 1 over 2n plus 1. We're starting with an n value of 1, and we're going to infinity. And so if we kind of look at this as a function per se, this initial value back here, if we plug in 0, this must be 1 here, right? So this is about 1/3 up. So this function here then, we're going to call 1 over 2x plus 1. So we're going to integrate that function, and we're going to make a determination of the area underneath that curve here. So we're going to integrate 1 over 2x plus 1 dx from 1 to infinity. Improper integral, so really what we're doing is we're saying take the limit as b goes to infinity, and we're going to integrate from 1 to b. And this is a natural log, so we've got the limit as b goes to infinity of the natural log of 2x plus 1, and then we have to take a look at the derivative here of 2x plus 1. The derivative is 2, so we need a reciprocal of the derivative out there. We're going to evaluate that from 1 to b. And so as we stick in the upper and lower bounds, we have the limit of 1/2 times the natural log of 2 times b plus 1 minus 1/2 the natural log of 2 times 1 plus 1, which is 3. And so putting infinity here now is not a problem, but the natural log of infinity happens to be infinity. So we're talking about infinity minus 1/2 the natural log of 3, which still ends up being infinity. So this area is infinitely large, and so since we have that dx, since the integral of, I should put the actual function in there, 2x plus 1 dx from 1 to infinity equals infinity, we really can't tell where the sum of the series goes. Is this sum, we know it's smaller, but how much smaller? Small enough to be finite? We don't know. So all we can say is, since this is infinitely large, then the sum of the series, as we add that up from n equals 1 to infinity, must also be undefined, or sometimes we say it does not exist. That's the same as saying it diverges. So if you think about it, we have a lot of different functions we can draw that are this non-increasing sort of shape. In fact, not only is it non-increasing, but it's definitely decreasing. It's not even staying the same. The question is, and I kind of call this a pinching off. It's pinching off against the x-axis. So the question is, how fast does it have to pinch off in order to get a finite area, as opposed to an infinite area like we have here? And that's the basis for this activity here.